It's my pleasure to introduce Steve Veldman. He is a machine learning engineer at Rotational Labs, and he specializes in computer vision, which is great given the topic of today's webinar. He earned his master's degree in data science from the University of Chicago. Actually, that's how we got to meet Steve. He participated in a machine learning hackathon while attending the university. And so we're really glad that he participated, and that's how we all kind of got to be introduced to him. Prior to joining Rotational, Steve worked in the manufacturing industry, and he gained a wealth of experience during that time. Outside of machine learning, Steve enjoys hiking, playing guitar, and adding to his vinyl record collection. And so now I will kick it over to Steve.
All right. Thank you. Thank you, Danielle. In the interest of factual accuracy, I'll have to, full disclosure, I have one class to go back and take to finish that master's. There's a scheduling conflict, and the class I need isn't going to be offered until June. So if you're a UChicago student in the class or in the webinar today, and you happen to be taking time series in the fall or in the summer, you may have me as a classmate. But anyway, thank you all for joining us today. Hopefully you find computer vision to be a fun way to spend your Friday lunch hour, or whatever hour this is, depending on where you are in the world. But I'm excited to talk about object detection and pose estimation with the YOLO algorithm today. I realize that everyone on the call could have some varying backgrounds, so I wanted to start with just a very quick high-level summary of some of the common computer vision problems that'll help give us a little bit of context around what we're going to talk about as we dive in. So the most simple computer vision problem really is image classification. What is this picture? Is this a picture of a cat? Is this a picture of a fish? Is this a picture of a cancerous skin lesion? Any kind of way you could frame that problem, but what is this picture? Object detection is a little more specific. What is in the picture and where? And image segmentation gets a little more specific than that. And I think on the next slide here, I've got some examples. So again, this is great credit to the academic article I pulled this picture from. Image classification, what is the picture of? This is a cat. Object detection, what is in this picture? There is a dog and two cats. Instance segmentation is a little more specific than that, because rather than just saying what is it and roughly where is it, we go into drawing these polygons that give it a little more precise localization. And then the final level of this is semantic segmentation, where you're not only applying a label to the objects in the picture, but you're applying a label to everything in the picture. So you'll see the background is labeled, but also the cats are just labeled as cat. So it's just sort of classifying pixel by pixel everything that's in there. You don't need all that background for today, but wanted to kind of, again, provide some context in which the problems we're going to look at today sit. What we're going to look at today specifically is the YOLO algorithm. So this is fundamentally an object detection algorithm, but we'll see how it's been sort of adapted and extended to apply to some of these other problems as well. It sort of made its name for being a faster alternative to region-based convolutional neural networks. Specifically because it only has to look once, as we'll see. It doesn't rely on this sliding window region proposal stage that our CNNs required, which required it to take multiple passes through an object before it could make predictions. So this is really nice for us because not only is that computationally efficient, but it opens up the possibility of using this algorithm for real-time inference on video streams, which we'll see, have a little fun with in a little bit here in a demo. So what we'll specifically be looking at is YOLO version 11. It is developed by a company called Ultralytics, which also maintains a very robust and well-documented API for using these models. So a little shout out to them for making it really easy to use this. They offer a version of YOLO that is pre-trained on Microsoft's Common Objects and Context, or COCO dataset. This is a large foundational dataset of somewhere around 300,000 images that are meticulously labeled. And so pre-training it on that gives it a lot of out of the box functionality that we'll see and have some fun with again here in a little bit. The asterisk is that technically the image classification version is trained on ImageNet, which is a different data set. But this version of YOLO supports multiple tasks. So we have the object detection that we talked about, which is sort of YOLO's claim to fame, but it extends that same architecture to support image segmentation. Oriented bounding boxes is sort of an advanced application of object detection. And then pose estimation is a really cool one, and we're going to have some fun playing around with that today. So I mentioned that API supports a bunch of other applications. So their library is very well documented on their website, and hopefully what we talk about today will give you the tools to get out there, look at their website, look at the documentation, and see how you can extend this to your own applications and your own problems pretty easily. So this is a quick example of what the different outputs from the YOLO model and Ultralytics will look like. You can see in the object detection, we've detected a car and some people, or a bus and some people in these images. The pose estimation actually only focuses on identifying people, but you'll see it also draws these key points. So this little stick figure that's been superimposed on all of these people in various yoga positions or yoga poses. It gets used in motion capture for film a lot, but it also can be really interesting and useful when you're looking at movement through an industrial space or some other interesting applications. So how does it work? You don't really need to know how it works under the hood in order to use the code and deploy a model like this, but you often need to know how it works under the hood to deploy it well, because when it's not behaving the way you want it to, understanding what's going on and sort of how the sausage is made can be very helpful. So we're going to do a very high level overview of what the YOLO algorithm actually does every time it's presented an image that it needs to predict on. As an example, we'll be using a picture from my last summer family vacation. So we took the kids to a bison farm, and that's what you're seeing here. So when YOLO looks at an image like this, it does a bunch of things very, very quickly. It immediately divides the grid into, or divides the image into a grid of squares. And for each grid, the first thing it will do is predict whether the center of an object exists in that square. So in our example here, in its single pass through the image, it identified that there were 3 objects, 2 people and 1 bison, and that these are the center of those objects. The next thing it will, and sort of simultaneous to this, because again, it's only doing it in one pass, it is then predicting bounding box coordinates, which exist, as we'll see later, in the form of the coordinate of the center of the object and then the height and the width of the box. And then it will apply class probabilities of what it thinks that object is. So in this case, our hypothetical YOLO application identified 2 people with a relatively high level of confidence and what it thinks is a bear and a relatively slightly lower degree of confidence. And the reason that it thinks this is a bear is because bison do not exist in the Microsoft COCO dataset. It found something that looked very similar to something that does exist in that dataset, which is a bear. But that is why, as we get into fine-tuning these models and adding additional classes, there's a lot of cool out-of-the-box functionality here, but part of what we need to do is tailor these to our application. So if you really need to identify bison, you'll need to do a little more than just use the out-of-the-box model. So the results for each image are represented as a tensor, and you get, or as a set of tensors, and you get 1 tensor per square. And the way this, so in this instance, we'll have 25 tensors for this image, and it will do this for every frame in a video, unless you've set it up to sample, every other frame or something like that. So the way this is broken down is the very first value in the tensor is the confidence that the center of an object exists in that box. Then we'll get the x coordinate and the y coordinate of what it believes is the center of the object. the height and the width of the object, and then class probabilities. So you can see for these three squares where it has detected an object, we get a fully populated tensor that describes what the model essentially has found. I've simplified this and only given us 3 classes because if I had to depict all 80 classes that the model is trained to identify, this would be a really messy slide. So for demonstration purposes, we'll pretend it only knows person, dog, and bear. And so you can see here for these 3 boxes, it populated the people pretty logically. It's very certain that something exists there. It has given coordinates for the center, is given box dimensions, and then probabilities where this is a little bit of a joke, but it is very confident that there's a person, that they're people. And if you've ever taken toddlers on vacation, you could understand why the model might accidentally mistake 2 toddlers for bears for a small probability. So the bison, it's less confident because maybe it's blending into the background a little bit more here. It still thinks there's something there, but not quite as confident. And then again, same box coordinate information, and then a probability for what it thinks it is. So again, it thinks it's a bear, thinks it could be a dog, is pretty sure it's not, or is very sure it's not a person. And then for the other grid squares, you will still get a tensor, but technically it's probably not an empty tensor because of the way it handles probabilities. But for demonstration purposes, we'll assume this is an empty tensor because we don't really care about it in this context. All right, another thing that's important to note if you're ever dealing with the raw output of a model like this is that the coordinates are actually measured not relative to the entire picture, but relative to their position within what's called the anchor box. So that's the individual grid square. And they're also measured from the top left corner as opposed to the bottom left corner, which is sort of what you're normally thinking of in like an XY plane that you've seen in like a math class or something like that. So little quirk, it's important to note if you ever have to sort of decipher what a model is actually doing with the raw results. All right, if you've made it through that, now we're into the fun stuff. We've got a little demo. This is probably a good time to pause and ask if anyone has any questions, though.
We actually do have a question, Steve.
Okay.
What if there are 2 objects in the same grid?
Yeah.
Yeah, let's start there.
That's a great and very good question. Let me see if I can easily tab back. So what it would actually do, again, I simplified this a little bit to make it processable, but the reason the results are a tensor is because even though this is more of like an array, it will, if the model is configured to identify multiple objects in the same box, then it will actually generate multiple arrays inside that tensor. So what we see here is sort of a 1, 2, 3, 4, 5, 6, 7, 8-dimensional array, I think. And so the tensor that is the result of each of these, for each of these anchor boxes, will contain more than one of these result arrays. And so we'll have a new center, a new object center, and new box dimensions and everything else that goes along with that. But that's a great question.
And to follow up on that, what if the object is significantly smaller than the grid square? Is it the same concept?
Yeah, I mean, the nice thing about the way it draws the boxes and everything, it would just, I hope you can see my mouse moving around. So pretend there's something up here, and it's a really, say there's a mouse or a gopher. I don't know. I don't think a gopher is in. Sorry, I just watched Caddyshack last night. Say there's a cat, and it would just have the center, drawn here and a little box around it, and it doesn't have to be bigger than the grid square for it to detect. It would just be a box that is nice and small. And as you start to see live inference on this, you'll see the grid squares really only matter to the algorithm. They don't matter that much to the way you'll see these results displayed. Does that answer that question?
I think so. And then the last one is around how does it resolve edge cases where the center's on the boundary?
Oh, where the center's on the boundary of the anchor box.
Yeah.
So that gets into a little more depth of how this works under the hood. Again, I tried to make this pretty high level and digestible for a bigger audience, but there are some techniques called non-max suppression and intersection over union that it uses to predict, because what it will actually do under the hood is predict multiple candidate dimensions for each one of these. It'll predict a couple different centers for this bison. It'll predict a couple different widths and heights for the bounding box. And then it goes through a mathematical process of selecting the center and the bounding box that is most likely. And so in the process of doing all of that, the algorithm will determine which center is say which anchor box it most likely belongs to.
That makes sense. And then I have a question. You mentioned how the bison in this image is misclassified.
Mm-hmm.
That said, classifying it as a bear is a relatively good guess. And then you mentioned how so how would we make it classify a bison? What would someone have to actually do to improve the prediction and have an accurate classification?
Yeah. So in order to accurately predict a bison would have to exist in the data that the model is trained on. So if I kind of translate it to an LLM context, this is a little bit like asking an LLM a question in Spanish when it's only been trained in English. Not quite, that's maybe not the perfect analogy, but this model has never seen a bison, but it's seen something that has a lot of the characteristics of a bison. It's big, it's brown, it's furry. And especially from this angle, it could easily be mistaken for a bear. And so it has managed to capture all of those characteristics of a bear and identify that this shares many of those. But in order to identify a bison, you would actually need to get labeled images of bison and add it to your training data and retrain the model.
So is that something I would do, for example, an image search on the internet to find images of bison, or would I want to go take my own images of bison?
I think it would depend on how many bison you have access to. And no, I mean, a lot of this is, we're getting into not experiment design, but I guess application design, where I think the specific how and why you needed to identify bison would probably factor into whether you could just collect images of bison off the internet and label them, or whether you would find a herd of bison somewhere and take pictures of them. If you are this bison ranch that we went to, you probably actually want to take a bunch of your pictures of your own bison, because the context of the images is going to be really important to training the model, and that will be the most appropriate and accurate context. And yeah, I think we'll get into the fine tuning once we get into the code a little bit. And so hopefully we can elaborate on that a little bit more. And then the process of curating a custom data set to train your model on is a little outside of the scope of this presentation, because I felt like we needed a lot of background before we got there. But if there's interest, anyone in the audience who wants to see that, send Edwin an email or post on the Rotational LinkedIn page and let them know you want me to come back and do that, because that would be a fun webinar to do. And I can give a little bit of a preview of that today.
Cool. Well, let's get to the demo.
All right. So the demo. Make sure I pull up the right screen here. All right. So I can at some point provide the code to the notebooks. It's all in a GitHub repo that everybody should be able to find easily with a link. But I put together a couple of simple Python scripts that can show some of this inference. And then we'll get into some notebooks where we're actually working a little more interactively with code. But one of the really cool things that you can do with this is live inference with a webcam. And so this should spin up nice and easily, because I was testing it this morning. So what it's actually doing right now is it is loading a local version of the pre-trained YOLO model. And here we go. All right. There's a little bit of a lag because of the internet, but can you guys all see? Oh, I guess not. Hold on. I have to change my screen share. 1 second. All right. So now, there we go. So there's going to be a little bit of a lag here, just because this is all running locally on my CPU, and we've got the webinar going. But you can see this is my webcam. Hi everyone. So you can see it identifies me as a person sitting here in my office. It identifies my mouse, although sometimes it thinks it's a cell phone or a remote. It probably identifies my cell phone correctly because it's seen a lot of those. I know it usually likes to call my Rubik's Cube a cell phone. So if you need to identify a Rubik's Cube, that's another example like the bison. You'd have to get into a little bit more. And then you can see it always thinks this pen is a toothbrush. And that's something if we don't run out of time, I have some data, image labeled pens. I've been playing around with trying to teach the model to correctly identify a pen. So this is pretty cool. You can see it's pretty good at identifying a lot of common objects, a lot of the stuff around my desk. Usually it's pretty good at calling a watch a clock. It doesn't actually know what a watch is, but again, these are the compromises you make when you only teach a model 80 things out of the whole world, and it does a pretty decent job of that. Now we've talked a little bit about the pose estimation models, and this is where it gets pretty cool. And is this showing up okay for everybody? Like, is this? I'm sure it's a little choppy, but is it coming through on the webinar?
It is.
Okay.
Yeah.
Great.
Yeah. Someone actually just mentioned that it identified some of the books on your bookshelf behind you. So that's pretty impressive.
Yeah. Like I said, there, what they were able to do with the large foundational data set is a great, great foundation. So this is the pose estimation model. It gets a little goofy when you're up really close, but you can see, you can find my eyes, my nose, my ears. It starts to kind of recognize my hands. If I get up, it will, you can kind of see how it does the stick figure on me.
Yeah.
Move around a little bit. So you can see there's some cool, knowing that it can do that in real time, there's some pretty interesting applications you can apply to it, but you'll also notice it does not identify my cell phone anymore. It is only focused on predicting people and then these key points. And if you need it to identify something other than a person, we will see that in some of the notebook tutorials. So I'm trying to think if there's anything else. Oh, so in addition to the webcam, you can also, let's see here. Yeah, so you can run, it on previously recorded video. There used to be a really cool way to, actually, no, we'll save this for the end. This is a good finale. I have the object detection model running on a clip from the Casino Royale film, a chase scene from that, and it's pretty fun to watch. But let's jump into the notebooks, because I see we're at about halfway through time, and I don't want to run out of I don't want to miss the sort of meat of the presentation. So last couple of things to talk about really quickly. This is super technical and may be of interest to some people, may not be of interest to everyone else. But one of the things that's important to note about this architecture is that this task specific head. So we talk about this in LLMs all the time, where after you deal with all of the hidden layers and you have some start to reach some semblance of an output, you have a task specific head that can do like sentiment analysis, or maybe its job is to generate text. We have a similar concept here where there's a task specific head that allows the same fundamental architecture to produce object detection models, or something different and maybe a little quirky, like the pose estimation that we just looked at. So I have a couple tutorials to go through here. The first one is just sort of out of the box inference with a couple pre-trained models to show what they can do. We'll try to move through those quickly because you've already sort of seen what out of the box inference looks like live on the webcam. And then the second notebook is a training fine-tuning exercise to teach the pose estimation model to do some very domain specific tasks. And then we may have a little teaser of that. How do you add a bison, or how do you add a pen to the foundation model kind of thing. So this is probably a good time. I can drop the link to this GitHub in the chat. So this repo has all the code that we're working through, in case you would like to follow along, or in case you'd like to play around with this on your own after the webinar is done. If anything is not working, or you have trouble getting it to do something different, or say you're just playing around with it and have a question, feel free to message me on LinkedIn, or reach out and let me know how this is working for you. So basic inference, pretty straightforward. We've loaded our required libraries. For object detection, basically what we're going to do is, so the purpose of this is we could use the COCO data set. We could use the data set that this model was trained on, but that doesn't really tell us whether it's a good model if it can, correctly identify the objects in the pictures that it was trained on. So I found this other data set. It's called the German traffic sign detection data set. It's available on Hugging Face. And what we're going to do here, I should probably switch over to, one of the reasons I'm doing this in Colab is because we have access to some limited but free GPU usage, and that, vision is a relatively compute heavy task. So just running it on CPU is not always very fun. So here we're gonna, we can download this data set. I gotta do all this. For the sake of keeping things moving, I think I'm just gonna talk through this while the Colab, I forgot that the Colab instance will have to reinstall all these libraries and everything as we go. So we're just gonna soldier on, since most of these have already, have readable output. But again, feel free to download these from GitHub, load them into Colab yourself and play around with them. And feel free to pester me on LinkedIn if they don't work, or if you have questions. So we're going to start by downloading this data set here from Hugging Face. And then we're going to load one of the pre-trained models. In this case, it's YOLO 11 small. So there's a nano, small, medium, large, and extra large. And this is just like large language models, where you have the 7 billion up to the, however many billion parameters we're up to now with the biggest models. And so the lighter weight ones tend to be a little more computationally efficient. They take a little less data to train, but also sort of the upper limit of what they can accomplish is a little lower. But we picked the small version. And here I just pulled 2 random images from this data set. So I picked the 1st and the 10th image in this data set. And the way this API works is it uses a results generator. So rather than sort of storing all of the predictions all at once, it creates an object that can call those results one at a time, which is very memory efficient when you're dealing with large data sets. So that's what this code is all working at. And then we're just using a for loop to iterate over each result. And what this does is these are images, again, that the model has never seen before, but it's able to identify with relative accuracy all these cars. Similarly here, you can see cars, a bunch of people. Pretty cool for pictures that it has never seen before. And we can do the same thing with the pose estimation model. In this case, I found a sports image data set, and again, we'll pull a couple images out of that data set and run inference on them with the pose estimation model this time. And you can see, I think this is field hockey, and then a baseball pitcher. You can see how it's pretty good at drawing the stick figures on them and creating these key point pose estimation predictions. Again, we can randomly sample some images from this data set, and you can see that the busier the image gets, the less helpful some of these things are. And then in this case over here, we've got a crowd of people. It is so overwhelmed with people, and it is so, poor resolution that it's not really coming up with anything useful at all. And that's a great way to demonstrate that there are limitations to these out of the box models. So if all you need to do is draw some stick figures on baseball players, it's great. But if you have a business case, some sort of use case where you need to analyze this image here, that's where machine learning engineers come in. why you need people like us. So another interesting thing to note, you can run inference on the entire data set all at once, and it goes very quickly. But then when you actually want to call them out or want to, pull individual observations out of that, it still sort of has to iterate through the whole object, even if you've indicated a couple random samples. So I won't make you all sit through and watch this churn, but this takes a couple minutes to get through all of this just to generate 3 random samples here. So little, I don't know if I'd call it a pro tip, but little shortcut might be that if there's specific images you need, you find their index in the data set and you pass it to them explicitly, which is what we actually did up here in this example. So we explicitly called out 3 items from the data set and only asked it to run inference on those. So that's a little down in the weeds, but it goes to kind of show that it's really easy to sort of get bogged down in computationally heavy tasks when you're doing this. And so sometimes you have to be creative in the way you ask the model to do its work if you don't want to just sort of sit and stare at it for a while it does its work. So any questions on that? I know that's like a lot of code we just scrolled through really fast. Again, hopefully everybody can poke around in the GitHub and ask me any questions offline if anything comes up. But are we good up to this point?
Yeah, I mean, we don't have any questions in the chat, but one question I do have is for those who are relatively new to working with computer vision models or YOLO specifically, given your experience, what are common pitfalls, maybe like 1 or 2, where you get tripped up or can be difficult to understand for, again, someone who's relatively new to working with computer vision models?
Yeah, I think the best advice I can give is like get really used to reading the documentation, because these more complex models, if you're just relying on Copilot or the Gemini assistant in Colab, I mean, it's great for debugging errors, but if you're asking it to like write code from start to finish, it's not going to be good at debugging its own errors. And reading the documentation in order to really understand how the API works and specifically how to properly ask it to do what you're trying to get it to do is helpful. Ultralytics has relatively good API documentation. So, you know, I think getting practice reading the documentation is like the best advice I can give. But because a lot of the things that are easy to get hung up on are like when you're dealing with this generator object, and how do you get the generator object to do exactly what you want? Are you trying to just get one result from one picture? Are you trying to process an entire video feed? Are you trying to just save when, you know, what timestamps in the video feed do these objects appear? Or are you trying to render a video with, you know, all these predictions sort of superimposed on it? And there are different, I say there are more and less ideal ways to do those things. Um, and some of it is just kind of coming up with a workflow that works for you, and it can be very use case dependent. But I think that is, I think that's the best advice I have, is like, do the old fashioned thing, and like, you know, normally I say read a book, but read the read the documentation. All right, so the next bit is where things start to get pretty fun. This is training models from brand new data sets. And in this case, what we're going to do is we're going to fine tune that pose estimation model for some different tasks. So in this case, the Ultralytics API supports some interesting data sets out of the box. And so I click through here and see what exactly we're dealing with. So I use these because they're really easy to work with, but can still demonstrate sort of the point. So in this case, someone put together a data set of about 27,000 images of hands annotated with the key points on the human hand. And so we're going to use this data set that looks something like this to train a model and see if we can get it to do what it's supposed to do. So to be absolutely clear, there is no out of the box pre-trained model for this task. The API provides a data set for you to play with, but what we it would take a while to do this in real time, so I did this ahead of time, and we're just going to load the model that I previously trained. But I did test this code again recently and make sure that it still works. So you should be able to train. You should be able to train this model yourself with a little bit of help from, you know, the Colab's free GPU access. So again, to walk through the code really simply, we just instantiate a version of the YOLO. In this case, I picked Nano, the smallest one, but you could plug in other things, the larger models if you want. I call it hand model because that's what we're going to train it for. But essentially for training, it's always better, in this case, to start with the pre-trained pose estimation model. Not always, but it is often better, often recommended to start with a pre-trained model and fine tune it from there. You can load an empty model with no weights and start from scratch, but that will probably take longer. And then here, the code for training the model is relatively simple. You use the model object and the train method, and you pass it the, in this case, because it's part of the API, you just need to give it the hand key points YAML as its thing. You might have to, if you're using your own data set, you'll have to give it like a file path to where the YAML file describing your data set is located. And then I set it for 30 epochs and told it what image size to sort of standardize everything to. So that's great. If you don't want to do this yourself, you can still play around with this by downloading the model I trained from my Hugging Face repo. And you can still, you know, play along at home. So optionally, if you've trained it yourself, you can save it, download it from the Colab file. And now we run some inference. So we have a couple images of hands that I pulled off of Wikimedia and some sort of orthotics website. And we can see if we run the same results generator code, we will actually, we can print those pictures of the hands with those key points superimposed on them. So pretty neat. But since, don't take my word for it blindly, just with some pre-run code cells, what we can do next is hop over here. And if I switch over to this version of the code and run it, it'll take a little while to spin up, but this will be sort of the same thing that we saw previously, except now it's not identifying me as a person. It has been trained to identify my hand. And you can see it does a pretty good job of identifying all my fingers. It gets a little wonky with the index finger. And it's not perfect because it does an okay job with a fist. The more you kind of give it things that are not familiar or not similar to the images it was trained on, the harder time it has. Like I noticed if you do like the little hand thing, like hand duck, it doesn't like that, probably because there are none of those examples in that data set. But again, this is pretty cool. The previous model we saw earlier could not do this. And so that is, there's probably all sorts of tasks for if you're a doctor that works in, orthopedics or something like that, where this would be interesting. The ability to sort of track range of motion for patients and all. You can probably, I'm not a doctor, but I can imagine a lot of interesting applications there. So that is, I thought that was pretty cool. Hopefully you guys enjoy it as well. To illustrate other cool things you can do, but also the limitations of this, another data set they have is a tiger pose data set. And this is not like a yoga thing, like a tiger pose. This is like actual tigers. So again, this code will instantiate a pre-trained model, train it on this tiger pose data set here. You can download the one that I did. I trained it for a lot more epochs because it was a lot harder task and a lot smaller data set. So we'll see how this one worked out. Found a couple of pictures of tigers on the internet, and we run the same sort of results generator process on it. And you can see it found this tiger key point identification is not great. And then the other two tigers, it didn't even recognize as tigers. Now, I will say that this is like a 300 image data set, which is woefully insignificant or insufficient for this kind of vision task. So that's why it's not working very well. But my guess is they only had so many experts available to label key points on tigers when generating this data set. But this is an interesting thing to look at. But we can again. And I'm really bummed. There used to be a way where you could run inference directly on YouTube videos. But now YouTube detects that as a bot and doesn't let you do it. So I had to download these videos, and I put some code for downloading sample YouTube videos, not to be abused for copyright infringement purposes, but only for instructional and educational purposes. You can download some short clips, and you can see, again, this is like some tigers interacting with each other. But you can see it doesn't do a very good job of identifying them at all. And this is actually running really slow because what it's currently doing is it's trying to predict on every frame. So if we change the code a little bit and we say, I'm trying to remember what I used on the other one. Yeah, vid stride equals 3. So now this is predicting on every frame, which kind of bogs it down a little bit. If we change it to predict, this vid stride argument tells it to predict on every third frame. And now we'll probably see it go a little faster. Now, if you were to pick 10, then it would like fast forward because it's going to only feed you every 10th frame. But you can see it's moving a little faster. Still the same problem though, right? It's identifying some of the tigers. Sometimes it's thinking 2 tigers or 1 tiger, and the key points are all over the place. And this is just to show that this is not magic. Like actually getting a model that works really well on a novel case or a domain specific use case actually involves a lot of hard work. And even with all the cool prepackaged stuff that we have access to in the AI world today, it's not, there's no like magic bullet that can solve all of our problems. But we have the tools available to begin solving these problems, and that is what I think is really cool. So that, I think, brings me to the end of sort of the very structured stuff. I have a couple examples that I can show of as an ongoing experiment, I'm working on getting a model to identify a pen, which is one of the things not included in the Cocoa data set. So I could show you kind of what's going on with there, or we could wrap up by watching this 007 chase scene with the with the inference on it. We might have time to do both, but it's probably a good time to stop and also ask for questions again.
Yeah, I have a question, Steve. I believe you mentioned that you were using the YOLO Nano model
Yes.
for the use case you just showed. If you use, for example, YOLO Large, what difference would that make?
And this is one of those things where I can probably predict, but there's a lot of like little quirks to the problem that may vary.
Right.
I think typically with a data set that small, like the Tiger data set was only 300 or so images.
Right.
You probably don't have enough data to really see significant improvement with a bigger model.
Okay.
I see where it's a lot like large language models where you really need if you think of like the data as the fuel and the model as like a car or a truck, right? You need a lot more fuel to power like a tractor trailer, like an 18-wheeler, than you need to power a Ford Pinto. So the small model is like the Ford Pinto.
Right.
And I guess hopefully that analogy sort of resonates with people.
Cool. Yeah, well, let's take a look at the car chase, and then if we have time, we'll do the pen.
Yeah. Let's wrap up with the car chase, I think, because that'll be a fun way to, and it's not even a car chase, it's a parkour chase. Rebecca has a question. Okay. What are the most common errors you find yourself debugging? So like many other machine learning applications, the most common errors I find myself debugging are tensor dimension, tensor size errors. So depending on what you're trying to do with the output of this model, if you're trying to do more than just run like a straight vanilla prediction with the API, you actually have to do something with the raw tensor outputs, then God forbid you're doing something in PyTorch and need to move it into TensorFlow, and the way those tensors are represented are different, or the tensors will be of different lengths sometimes. Like the question about how to predict multiple objects in the same anchor box. So the tensors will be different sizes based on, or different dimensions based on how many objects are located or are found in a anchor box. And so, having to pad all of those tensors and figure out how, what is sufficient padding, but not creating extra data overhead. Problems that are probably very familiar in similar contexts to people who deal with LLMs, right? Where you need some consistency there. Let's see. Lynn. Hey, Lynn.
Hey, Steve.
Yeah. How are you doing today?
Great. How are you doing? Thank you so
Good.
much for the presentation.
So you have a question about fine-tuning the model with other data sets. Sure.
Yeah, I feel like that's pretty more widely used in the industry. And if you could talk more about that, that would be great.
Yeah. So that the code for the pose estimation stuff kind of holds for anything. Again, I just pulled the out of the box data sets because they're easy to work with inside a collab notebook. And I think this is a webinar that I hope to develop and maybe present later this year, is how do you actually talk a little bit more about sort of harvesting your own data set and the process of annotating data and organizing it in a way to get it to, there's a lot of hard work that someone did to get this data set to the point where you could just download it via an API like this. Is that kind of what you're
Exactly.
talking about?
Yeah, like you have to put in the same format as that hand dash key points the YAM, right? I
Yeah.
mean, that takes a lot of time.
Yep.
Yeah, absolutely. And so I think that is, I think, the biggest challenge if you're going to fine tune a model on your own data, annotating it well, and then getting those annotations into a format that's easy, not easy to work with, that matches what the model is expecting. We actually got to do this for a client with one of our projects at Rotational earlier this year, where we went out into the wild and captured a novel data set, and then actually annotated it ourselves, organized the annotations, created the whole structured data set object, and then fine-tuned an object detection model on it. And so if there's interest in going kind of deeper into that, I think that's probably a whole webinar in itself that I'd actually be really excited to give.
Me too. I'll vote for that.
Okay, awesome.
Yeah, because the actual training fine tuning step in the code is actually just model.train. It's that simple, right?
Yeah,
Because thanks to its API, you literally just do model.train.
yeah, and there's some hyperparameters you can play with in terms of, like, in this case we just picked a standard image size of 640 by 640. The project we worked on recently involved large high resolution images where sometimes what we were interested in was far back in the frame. So I actually played around with this image size to figure out how big could I keep the images and still have everything fit in memory with the GPU that I was using. So it was not the most computationally efficient way to do it, but it did give us better results in terms of being able to detect what we were looking for further back in the video frame. And there's a lot of, if you dig into the Ultralytics API, there's a lot of other, the documentation talks about a lot of other hyperparameters that you can tune when you're trying to kind of squeeze extra performance out of a model. But you're right, the bulk of it is not in running this line of code. The bulk of it is in actually finding and preparing a suitable data set to train your model on.
Yeah, I'm looking forward to that later
Awesome.
this year.
Cool.
Maybe. Thank you so much.
Thank you. And Rebecca says, how do we do model comparison with computer vision? We're considering two different base models for the bear detection model. How would you evaluate and compare them to decide which is best? So like most AI related tasks with unstructured data, there are some metrics you can look at. And so if you're, if you're looking at comparing two similar models for the same task, specifically if you're looking at two different sizes of the same YOLO model, for example, there's some pretty clear-cut metrics you can look at. And you can, there's the model results will give you some metrics around like mean average precision, which has to do with how accurately the bounding boxes are drawn, or how tightly around the object they're drawn. There's also just, you can generate a confusion matrix of, how many times did it accurately predict an object. The thing that's really interesting and makes it really tricky to do with vision, though, is if you're looking at a video, the meaningful metric isn't necessarily in every single frame how often did it detect the object, but it's more, did it detect the object at all? Or what percentage of frames did it detect the object in? Or in a lot of use cases, it's how quickly did it detect the object. So you might have a model that can find an object in a video stream, but maybe it's important, if it's say it's a defective item on an assembly line. Well, you don't want to identify that defective item after it's been packaged or when it's like far down the line. You want to catch it early. That's a little bit of a contrived example because it would be more complicated than that in practice. But say you're trying to, I don't know, let's say you live in Australia where they've got kangaroos running around everywhere and you're trying to detect when a kangaroo wanders into a shopping mall. This is a very contrived example, but I'm trying not to talk about any specific projects that we have going on because those would be the more more relevant examples. How quickly you found that kangaroo in the shopping mall is just as important as whether it found the kangaroo at all. I know that's a little bit of a silly example, but does that help? Yeah. Kangaroos are dangerous. All right, we have the question. I found fine-tuning YOLO model not so straightforward because of the specific way the data directories need to be structured. Yeah, that is very true. The different formats for image data sets that different models expect is a big challenge. And that is sort of the data engineering or the data wrangling side of things that, it is very true what they tell you in school where they say 80% of your time as a data scientist is going to be just processing and formatting data. Not because that's the hardest part of the job, but because that's the part of the job that has to be done right if anything else is going to work. So I hope I'm pronouncing your name right, Sarthak. Yeah, if that's definitely something we can get into in more detail in a future webinar, if that's something you'd like to see, because that is, I think when Edwin asked what are the common sort of struggles and pitfalls, just getting the data set up correctly is definitely where you'll probably spend a lot of your time. The training itself, you just kind of, once you get it set up, you hit go and then you let it run for a couple of hours while you go have dinner or something and come back later and see how it did. But the hard work is kind of everything leading up to that hit train moment. Well, if we don't have any other questions, I guess we're probably a little over time, but do you guys want to see the bond thing real quick?
Yeah, absolutely. And while Steve is pulling that up, just a few brief announcements. So as I posted in the chat, everyone will receive a link to the recording as well as the slides. So we'll share that. We will have our next tech talk coming up in June, most likely, so stay tuned. And then just a few quick announcements about some recent publications that are coming out from our team. Prima Roman and Patrick Desiel, two of our machine learning engineers, are working on a book called Real-Time Machine Learning that will be out relatively soon. That's through Manning Books. And then our CTO, Rebecca Bilro, is working on a book called Apache Hudi, The Definitive Guide, and that should be out soon as well. So just a few announcements, and then let's see the demo, Steve, and we can wrap it up.
Awesome. So I think it should be running for everybody to see now.
Yeah.
You can see it's picking up these trucks. Again, emphasis on this is the out of the box model, completely pre-trained. So it's gonna do some quirky things. I think there's a spot here where it thinks something is a refrigerator, if I remember right. Yeah, it thinks his gun is a sandwich at one point. So again, these things there's a lot of cool things that you can do right out of the box, but they are not production ready straight out of the box here. But it is pretty cool still to see. So yeah, I think that hopefully a good job of giving everyone a little taste of what this can do and gives you some foundational code to play around with that we can maybe build on in the future.
Yeah, absolutely. Thank you, Steve. Really appreciate the deep dive into computer vision. I know I learned a lot. I think everyone on this Tech Talk learned a lot as well, and a lot of great questions, a lot of great comments. Thank you, everyone, for attending. We appreciate your participation. Like I said, we'll follow up with the materials, and we'll see you next time. Thank you, and have a wonderful weekend. Thanks, Steve.
Thank you, everybody.